In an asymptotic analysis, we're describing the behavior of a function. We're describing the worst case running time of our algorithm as a function of our input size for large enough values of n. So we're considering already that n is large. And when we express this, we use only the highest order term in the expression to show the exact runtime. So remember our array max algorithm, it had exactly 7n minus 1 primitive operations, but instead of specifying that all out exactly, since the only thing we really care is about the growth rate, we'll describe that as a linear function. So in that case, we would say it was big O of n. So in other instances, instead of saying the exact runtime, we'll say that it's big O of some function, n squared, n cubed, not including those lower order terms or constant factors. So this is asymptotic notation. So we have a few of them that we're going to see. Here we have big O, let me put big O, big omega, theta, little o, and little omega. And the way that we would say this is we have some function of n, and we'll say that f of n, this is how many primitive operations we have in the worst case, f of n is big O of n squared. So which asymptotic notation we use here, which one of these, if it's big O, big omega, theta, little o, or little omega, each one of these describes a different way in which f of n grows with the function which is inside of the parentheses here. So for example, big O, which we'll see, this is saying that f of n is asymptotically upper bounded by the function n squared. So each of these different asymptotic notations describe a different rate of growth relation between f of n and this set of functions. So let's see formally the definition of big O. So if we have a given function, g of n, big O of g of n is actually a set of functions. So this is formally described here. We have big O of g of n is a set of functions so that there is some positive constant c, and there is some positive constant n sub 0, so that for all values of n greater than this n sub 0, we have that f of n is upper bounded by that constant c times g of n. So we've got that there is some constant c which we can multiply by our function g of n, so that at some starting point here, this is our n sub 0, right? At some starting point, doesn't matter what comes earlier than that, because we care for large enough values of n. So we just care that there is some starting point, so that from this point forward, and every value of n after that, if we compare the functions c times g of n to f of n is less than or equal to this value. So for everything from here on afterwards, here we've got c times g of n. At each one of these instances of n, starting at n sub 0 and afterwards, we have that this function here is less than or equal to its corresponding value c times g of n. Right? So big O is intuitively, this is describing the set of all functions whose rate of growth is the same as or lower than this value here, than g of n. So g of n is an upper bound for f of n. So if we say, for example, that f of n is big O of g of n, we're saying that g of n is an asymptotic upper bound for f of n. So because big O g of n is actually a set of functions, technically, you'll see this kind of both ways. Technically, we would write that f of n belongs to the set of functions big O of g of n, using this notation here. But because when we describe this in English, we actually say f of n is big O of g of n, you'll also see this equality sign here. So these are both equivalent. Technically, the top one is correct, but it is so common to use the bottom one that either one of these is okay. So when we say f of n is big O of g of n, we're saying that f of n is asymptotically upper bound by g of n. G of n is an upper bound for f of n. This is kind of like saying, so this isn't exactly the same, but this is kind of like saying that f of n is less than or equal to g of n, if we were to put this kind of in other terms. So this isn't exactly the same thing, but it's like saying that this, right? So we can use this in order to rank functions according to their long-term growth rate. So for example, here we have, this is just the same definition that we had earlier for big O of g of n. So the following functions, everything that we have here is big O of n. So if we have f of n is equal to 2n plus 10, this is big O of n. If we have f of n is n plus 1, this is also big O of n. Each one of these functions are big O of n, meaning that n is an asymptotic upper bound for these functions. We're essentially saying that these functions are linear. So if you notice that, as I mentioned, we don't care about lower order terms. We also don't care about constant coefficients. So in each one of these functions, if you were to get rid of those lower order terms, for example, 2n grows faster than 10. So 10 is a lower order term, we get rid of that. And we get rid of any constant coefficients like 2. The only thing we're left with is n. So this is a quick way that we could very quickly evaluate the big O notation for some function. Now everything on the right side here, we have that these are all big O of n squared. These are quadratic functions. So if we have n squared plus n, this function is big O of n squared. N squared plus 1, this is also big O of n squared. All of these functions belong to the set big O of n squared. Now notice that I have here f of n, when this is equal to n to the power of 1.99, this is also big O of n squared. So this is still upper bounded by n squared. If we were to kind of plot these, we may have n to the power of 1.99 goes like this, and n squared goes like this. Right? So n squared is still an asymptotic upper bound. Now, this doesn't go both ways here. So we do have that for any one of these functions here, hang on. Okay, so for any of these functions here, all of them are big O of n, and because they're upper bounded by n, then they're also upper bounded by n squared. So we could also say, all right, 2n plus 10, this is big O of n, but this is also big O of n squared. So because n is a slower growing function than n squared, if I have something which is already upper bounded by n, then it's also upper bounded by some faster growing function like n squared. So each one of these, they're big O of n, but they're also big O of n squared. But we wouldn't be able to go kind of the other direction. Each one of these functions are big O of n squared, but we would not be able to say that any one of them is big O of n. And the reason for that is there is no constant that we can come up with, so that f of n for any one of these, that n squared plus 1 is less than or equal to some constant times n. We would have to be able to show that in order to say that this function is big O of n. So this isn't possible for any of the functions on the right. Okay, so we want to be able to say, for some algorithm, we express that algorithm in pseudocode. We can count up how many primitive operations it has as a function of n, and then we take that function and we put it in big O notation in order to quickly evaluate whether it's efficient or not. So rather than saying that some algorithm requires 10n squared plus 300n minus 5 primitive operations, instead we would just say this algorithm runs in big O of n squared time. So let's see, how would we actually come up with this big O notation? So our rules for this are that we drop any lower order terms. So for example, if we have a polynomial of degree d, so this means, let's say we have a polynomial of degree 3. This means we've got n cubed plus n squared plus n plus, some constant, I don't know, 1 or something. So this is a polynomial of degree 3. Then this function is big O of n to the highest degree. So that means that this is big O of n cubed, right? We're taking whatever that highest term is, the highest order term. So n cubed here is the dominant term, right? This is most responsible for our growth rate. The other remaining functions are lower order terms. They don't contribute as much to the growth rate. So that's one rule. Drop any lower order terms. If we had, for example, let me do one other, n to the 5th power plus n to the 3rd power plus 5, let's say. Again, these are lower order terms. N to the 5th power is the highest order term, so we could say that this function is big O of n to the 5th power. So that's our first rule. Secondly, we drop any constant factors. So if we have 3n plus 5, we can already, from our first rule, get rid of 5 because that's a lower order term. And what we're left with is this 3n. But 3 is a constant factor. This is a coefficient to n. So rather than saying this is big O of 3n, we get rid of this constant factor 3 as well. The only thing we're left with is n. So we'd say that 3n plus 5 is big O of n, rather than saying it's big O of 3n. Right? So we don't use these constant factors. If we had, let me give one other example here. Let's say we had 8n cubed plus 5n minus 40. So again, we get rid of these lower order terms. We drop this constant factor 8. This function, 8n cubed plus 5n minus 40, this function is big O of n cubed. Okay, so again, the purpose of this is to sort of simplify how we express the running time of some algorithm. We have an algorithm which has this many primitive operations exactly. We don't care about the exact number of primitive operations. Much better, more important for us is we care about the growth rate. So for large values of n, how will this change? Well, this is a cubic function. This is big O of n to the 3rd power. Right? Okay, and thirdly, we want to use the smallest possible class of functions. So we saw in the previous slide that the function 2n, this is big O of n, this is a linear function, but because it's big O of n, it's also big O of n squared, and it's big O of n cubed, and it's big O of n to the 4th power. So technically this is correct. 2n is upper bounded by all of these functions. However, the smallest possible class of functions, the one which has the smallest growth rate, is to say that 2n is big O of n. Right? So the reason why we want to do this is because we're using this to represent the runtime of some algorithm. And if you have an algorithm and it requires, let's say, 5n primitive operations, much better for you to say that your algorithm runs in big O of n time, because that is a good representation of its growth rate. So it would be technically correct for you to say it's big O of n to the 5th power, but that's a little bit misleading because then it kind of suggests that your algorithm is slower than what it actually is. So always use the smallest possible class of functions. Okay. There's another theorem in your book, Theorem 1.7, which will be particularly helpful. And for this, the reason why these kind of 3 points in particular It also includes the 3 items I mentioned earlier, but a few other important ones. These rules will help for you to identify if you have already 2 different algorithms, algorithm A and algorithm B. And you know for each of them, for example, algorithm A requires n to the 5th power primitive operations, and algorithm B requires 2 to the nth power primitive operations. And you have these 2 different functions. How do you know between them, how do you compare which one is slower growing, which one is more efficient? So that's what these last 3 are for. So let me here erase this. Let's do this one first. So what does this mean really? So this is saying for any fixed x, and this is where our x appears, and any a, so this is just some constant, each of these are just some constants, a here, we know that n to the power of x is big O of a to the power of n. This means that if we pick any value of x as long as it's greater than 0, and any value of a as long as it's greater than 1, then this always holds. So let's say you have a function, and I'm going to write it up here, n squared, and you had another function, let's say 3 to the nth power. Because of this rule, we know that n squared grows at a slower rate than 3 to the nth power, because n squared is big O of 3 to the nth power. Okay? Or you could also use this to say n to the power of 4.3. This grows slower, significantly slower, albeit, but it does grow slower than 2.1 to the nth power. Okay? So you can pick any value of x and any value of a in order to kind of satisfy this, as long as x is greater than 0 and a is greater than 1. So this gives a lot of different examples on how you can compare if you have some function here and some other function here, which one is slower growing. This is definitely not the smallest class of functions for which we would represent n squared, if that's all that we had. If we had an algorithm which ran an n squared, that many primitive operations, we would definitely say this algorithm is big O of n squared. But the purpose of these kind of 3 points are to, if you have 2 different algorithms already, one which runs in n squared and one which runs in 3 to the nth power, how you can evaluate which one is slower growing. So n squared is much slower growing, but this gives us a way that we can find out which one's slower. Okay, so that's the first one. For the second one here, we have for any fixed x greater than 0, log of n to the xth power is big O of log n. So if you'll remember kind of why this is true, let me put that up here first. If we have log of any base, but usually when we say log here we mean base 2, but it doesn't matter which base we're using. If we have log of n to the xth power, any x greater than 0, this is equal to x log n. Okay. These 2 things are equivalent. So because x is just some constant number, it doesn't depend on n at all, when we put this in big O notation, we'll end up getting rid of that constant coefficient. Right? So log of n to any power is log n. That's what this second part says. So if we had, let me do an example here, if we had log base 2 of n to the 5th power, this is big O of log n. So again, this is an asymptotic upper bound. So another way of viewing this is log of n to the 5th power grows slower than log n. Or no faster than. Okay, let's do the third one here. So for any x greater than 0 and y greater than 0, again, these are just some fixed values. You can pick anything. They're not dependent on n. We have log to the power of x of n is big O of n to the power of y. So this formula here, log to the power of x of n, this is the same as taking the entirety of log n and taking all of that to the x power. So this is not the same as what we had before, where we had log of x to some power. It's not the same as that, right? So this function here is equivalent to taking the entirety of log n to the x power. And what we're saying is that if we took log to any power, let's say we had log to the 1,000th power even, so you can pick anything, log of n all to the 1,000th power, this still grows at a slower rate than if we were to pick n to any power. Let's say we just pick n to the first power. So this says that any power of a logarithm grows at a slower rate than any power of n. Or to give another example here, so let's say we picked x to be 5, so log 5 of n, and y to be 0.001. Okay? This is big O of n to the power of 0.001. So this seems like a pretty slow growing function, right? N to the power of 0.001, but it doesn't matter which power of a logarithm we have, any logarithmic power grows slower than any power of n. Okay? So there's a lot of other things you can put in here, just plugging in for x and y, but this just gives you a way that you can compare, for example, logarithms to n. So this also gives us, this third theorem also gives us that log n grows at a slower rate than just n. Okay. Okay, I wanted to take a moment and do a few other examples with you guys. So I have some here. I've got 54n cubed plus 10n minus 500, 3 log n plus n, 2n log n plus n to the power of 0.01 plus 5 log squared n. And if you can see, this is n plus 5n squared plus n log n plus log of log n, and 32. Now normally, I would take this time to put this up on the board and then give you all time to figure out what the big O notation is for each of these functions. So imagine each one of these is that we have some algorithm, the total number of primitive operations that it has, that it executes, is this, for example. Express the running time of that algorithm in big O notation. So take a moment, pause the video, and try and solve some of these on your own, and then I'm going to put the solutions up here and talk through why those are the solutions. So go ahead and pause the video and then hit play when you're ready to go. So let's do the first one. So again, we're going to drop any lower order terms and constant coefficients. So the highest order term in this is based on which one of these has the highest power of n, and that's definitely n cubed. So we can get rid of these lower order terms and get rid of the constant coefficient, 54 here. So this function runs in big O of n cubed time. This is a 3. For part B, now we have to decide which one of these is the higher order term, which one is dominating. Okay? So which one has the faster growth rate. So if we were to compare log n versus n, remember that's one of the bullet points from theorem 1.7, is that log n grows slower than n. In fact, any logarithmic power grows slower than any polynomial. So n is the dominant term here. So now that we get rid of any lower order terms, when we put this in big O notation, this is big O of n. The next function, 2n log n plus n. So here again, we have to figure out which one of these is the dominant term. Definitely we can get rid of the 2 because that's a constant coefficient. But between n log n and n, just by itself, which one grows faster. Now, log n just by itself grows slower than n just by itself. But here we have more than just that. We have n times log n compared to n times nothing else. So you could kind of think of this as being n times 1. Right? They have one common term, which is this n. Both of them have n. The only difference between them is a factor of this one additionally has log n. Log n by itself is slow growing, but if we are comparing these two, here we're multiplying by 1, that's not growing at all, 1, versus log n, this is slow growing, but it's still faster growing than 1. So in this case, n log n is our dominant term. So when we put this in big O notation, this will be n log n. Okay, for the next one. We have n to the power of 0.01 plus 5 log squared n. So again, if we go back to theorem 1.7, we have that any logarithmic power grows slower than any polynomial, n to any power, even though this is a really small power. So this is our faster growing function. So we're going to write, because we want to use the smallest possible class of functions, we're going to use exactly this power here. So this is big O of n to the power of 0.01. Okay, for the next one here, we have n plus 5n squared plus n log n. Now we could compare, let's just take between the first two, right? Definitely we're going to get rid of this 5, so let's just think n versus n squared. This is the higher power, so this is faster growing. So just between these two, this is the dominant term. Between n squared and n log n, again, we can kind of think of this as what common terms do they have? Both of them have 1n. This one has 2n squared. This one has this other log n. So we can use theorem 1.7 again to see that log n just by itself grows at a slower rate than n just by itself, if we were to look at this as this n squared as being an n times n. So their common parts here are just n. The only parts that are different are this other n and log n. And since log n grows slower than n, this is our dominant term, our fastest growing term. So this is big O of n squared. Okay, and lastly here, oops, second to last, we have log n plus log of log n. So note that this is not log squared of n. We're taking the logarithm of whatever the result of log n is. So log n just by itself is a slow growing function. But when we compare this to this one here, since we're not multiplying them, we're actually taking the logarithm of a logarithm. So log n by itself is pretty slow growing, and then we use that as the input to our logarithmic function. So we end up getting an even slower growing function than log n just by itself. So log n is the dominant term here, so this is big O of log n. And then the last thing that we have is 32. So this doesn't depend on n at all. This is a constant function, so this is big O of just 1. So how did you do? Hopefully you got them all right. Let me know if you have any questions. As always, post on Piazza.